And then using those groups, we can build these operads called the parenthesized Braid and Cactus operads. And then we can classify braided monoidal and Coboundry categories as algebras over these operads. So to begin, I'm going to talk about the topology and algebra side of the braids. The way I want you to think of the configuration space of endpoints in the complex plane is that this disk here will be a copy of the complex plane if you want. And then a single point in this configuration space is a copy of C with n marked points on it. And in this way, we can imagine a path in this space as going from one configuration here to another, with these strands representing the sort of trajectory of our marked points. So if you squint your eyes a little bit, you might be able to imagine how we can use this to build a diagrammatic language for the homotopy group, where we can think of these dots at the top here as our marked points. And then we can draw a sort of braid, maybe something like this, which shows some homotopy class of loop. How the diagrammatic calculus works is to show multiplication of braids. I simply stack the braids, so I'd have maybe something like this. And this actually fully encapsulates how the braid groups work. If you just think of this intuitively, moving around strands one on top of the other, you get an idea of what braids would be equal to other braids. But we do have a group presentation for these things, which can be seen here. So again, the braid groups are the fundamental group of this configuration space, but we can show them as a group presentation like this, where Bn is our nth braid group, and it's generated by these elements Bi. And I think I might be talking about too much stuff to fully go over these rules, but I do have them written here, and you can look them up as the Artin braid group if you'd like. Each of these braids carries with it an underlying permutation. And the way that we figure this out, if I draw a braid like this, maybe, and then label the tops of these things, 2, 3, 4, and then follow where the strands take me like this, then I can figure out what the underlying permutation is. And in this case, the underlying permutation for alpha is the permutation that takes 1, 2, 3, 4 to 2, 1, 3, 4. This defines a surjective group homomorphism from the nth braid group to the nth symmetric group. And we can define the pure braid group as the kernel of this homomorphism. And the way we should think about pure braids is that they're going to be braids that just take the first place back to the first place, no matter what weird trajectory it goes down, and so forth for all of the different places. So for the topology side of cactuses or cacti, it's not as clean and easy to visualize. What we have are, as points in this moduli space, real curves that are marked. And so they look a bit like cactuses, and that's where the name cactus group comes from. So we have these sort of leaves with spines that are the marked points. And then a homotopy class of loop might look something like this, or a homotopy class of path, where you start with just some marked points on a loop, and then you bubble off some sub-interval of the marked points like this. We then spin those around so that they're now in reverse order, 4 through 2, and then reabsorb it back into the original starting point. This is what a homotopy class looks like. And that's where this group comes from, which is the cactus group. And we can present it this way. Unfortunately, there wasn't a nice diagrammatic language for this the way we had with braids. So we had to work with this presentation here. How it works is the nth cactus group, or the cactus group on n fruit, which I like because I think that's adorable, is generated by elements Sij, where I is less than j, and they're both between 1 and n. Every generator is its own inverse, which is what this rule says here. We have that Sij SPQ is equal to SPQ Sij just when these intervals are completely disjoint. And then we have Sij SPQ is equal to SPQ Si plus j minus q comma I plus j minus p. And this is just when the interval I through j is a subinterval of p through q. This rule is the main reason I desired some sort of diagrammatic calculus, because it's not fun to play with when you get like big long strings of letters in this group and trying to figure out what's equal to what. And so I came up with a diagrammatic language, which I call the Cactus calculus. And I'll show you exactly how this works. So a generating element is Sij of some form. The way this is going to work is, say we're in the fourth Cactus group, then I will draw 4 vertical strands. And then the element S14 as an example, I will simply draw by drawing a rung horizontally from the first to fourth strand. So then the first rule of the Cactus group, which says that generating elements are their own inverses, can be shown in this visual calculus like this. If I have 2 horizontal rungs of identical placement and length, they can collide with one another and disappear. So that's what this says here. It says if I have these 2 rungs next to each other, they look identical, they can go away. The second rule is about that disjointness of intervals. And what it says here is that this is the same thing as doing this, which should be fairly obvious. The idea is we can move these horizontal rungs, right? Basically, if 2 rungs don't impede each other's paths at all, you can just move them past each other freely. The last rule, which was that weird arithmetic one that's not fun to play with, works like this. I have S14, S13 here. This is going to be the same thing as S24, S14 here. And how this works is, if I have a smaller rung that's completely within the placement of a larger rung, meaning it's not overlapping, it's completely within, I can move it past the larger rung so long as I flip it over the median of the larger rung. So that's what it looks like here. I took this smaller one here, I put it below the larger one, but I had to flip it over the median, so it ends up over here. So one really nice thing about, well, first of all, this calculus is really great for just doing computations in these Cactus groups, because before we had to look at these letters and try to figure out all the arithmetic with that, this makes it a lot quicker. You can just look and move things around fairly quickly. Another nice thing about this is it allows us to fairly quickly figure out what the underlying permutation of a given Cactus group element is. And I'll show you exactly what I mean by that. So here we have S12, S24, S34, S25, S15. And if I were to look at this word here, I would have no idea what the underlying permutation is. I would have a very hard time looking at that and figuring out where it's going to in this metric group. How we use the Cactus calculus to figure this out is we sort of trace the trajectory of these vertical rungs. And I'll show you what I mean. If we start at 1, I'm basically going to go down until I hit a horizontal rung. Once I do, I will go over the median, flip over the median of that rung. So I end up all the way at the end over here in this case. I keep going down, flip over the median here just means flip over by 1. Down, flip down, flip down, flip down, and 1 ends up here. We can repeat this process for all of them. So in this one, it would go over to here, down, over to here, down, over. That is the median, so there's no flipping necessary, and 2 goes down. We can do the same for 3. And 4. And 5 will end up in that last slot, but let's just show that it works. And 5 is here. So now I know that this Cactus group element has the underlying permutation that sends 1, 2, 3, 4, 5 to 1, 4, 2, 5, 3. Awesome. So now that we've covered the topology and algebra sides of both the braids and cacti, we can move on to the operad and category side of things. So I want to construct an operad that is in the category of categories, which I'm going to call the parenthesized braid operad. So for those of you who are not familiar with operads, We're going to just think of this as a collection of categories, P, A, B, N, for all n greater than or equal to 0. And then composition, operatic composition here is going to be done by something called cabling, which I will describe below. But before I get there, let's just go over what are these categories P, A, B, N. So as an example, in the category PAB4, I have as objects parenthesized permutations of 4 letters. And what that means is I pick some permutation of 4 letters, in this case, X1, X3, X2, X4, and then I put parentheses around them. And the rule is if I have n letters, I need n minus 2 parentheses. And the way you want to think of this is as associativity. We need to know how we are associating these things. So if I have this object here and this object here, then what is the HOM set between these two objects? Well, it's going to be every braid that corroborates these underlying permutations. And so let me show you exactly what I mean by that. If I draw a braid here, we just need to make sure that X1 goes to X1 and so forth. So I might take X2 like this. X3 maybe goes under that one or over that one and then under this one, and then X4 goes straight down. This would be an example of a morphism between these two objects. So alpha would be in this HOM set. Great. So for those of you who aren't familiar with Operads, the operatic composition, basically what I want to be able to do is I want to be able to plug in one of these braids into another one. I want to be able to take one of the strands of my braids and I want to take a whole other braid and put it there. And that's this process called cabling. So here I have 2 braids and I want to take the green one and I want to plug it into the second slot of the first one. I've drawn that as composition over 2 like this. So the first part is fairly obvious. I just take that strand and throw in the whole green braid. And then what I need to do is I need to sort of re-index my permutations on the top. So I replaced X1 with something that has 3 letters, which means that my X2 needs to now be an X5, like this. Otherwise, I can basically write down what the other braid is doing. Like this. But as you can see, I now have 4 letters, and the rule was I need to then have 2 sets of parentheses. And the way we do this is we just put parentheses around the entire braid that we plugged in. And that is our composition for our Operad PAB. So there's this nice connection between this Operad PAB and braided monodal categories. So I'm going to briefly explain what a braided monodal category is, and we'll move on from there. So a braided monodal category is a monoidal category, meaning that it has some notion of multiplication within itself, some functor from C cross C to C. And we're going to say the image of X comma Y, we're going to call it X tensor Y. These are sometimes called tensor categories for a reason. A braided monodal category is one that's equipped with natural isomorphisms from X tensor Y to Y tensor X, such that they fit into these 2 pentagon diagrams. The maps that say A there are associators. They're isomorphisms between different choices of parentheses or associations. So this leads to the theorem. A category C is a braided monodal category if and only if it is an algebra over this PAB operad. And this, without the language of operads, was first shown in the original braided monodal categories paper by Joyal and Street. There's a proof of this for strictly associative braided monodal categories in Natalie Wall's thesis. And then there's a treatment in full generality for weakly associative braided monodal categories in Donald Yao's book on operads with group equivariance. Okay, so I wanted to set out and build a parenthesized cactus operad. And so the first parts of this were fairly simple. I'm just going to build it the same way I did the braid one, where my objects are going to be these parenthesized permutations. My morphisms are going to be cactus group elements that corroborate the underlying permutations of those objects. But I wasn't sure exactly what composition would be. So what is cabling for cacti? So it's going to be fairly similar, where once again, I'm trying to be able to put a whole cactus group element into a single slot of some other cactus group element. Here I've drawn two. So the first part is obvious. I'm just going to take this whole thing and I'm going to plug it in the top over here. But we need to be careful because I can't just do that. I need to follow the whole trajectory of this strand the way that the braids did before. And so we need to sort of look at our cactus group element here and see where that second slot is going, as I've drawn with this pink line here. So that's what's going on with these green bits here, is I'm keeping track of where this whole cactus group element is going. The second thing is that whenever I have over here a horizontal rung hitting this trajectory, when it hits a whole cactus group element, it's actually going to flip the order of that thing. And I need to undo that. And so that's what these red bars are doing here. And then otherwise, it's the same as cabling for braids, where I have the same sort of re-indexing of my parenthesized permutations. We can also use the Cactus calculus to simplify this diagram quite a bit. As we can see, for these two horizontal rungs at the top here, they're identical and they're next to each other, so they can collide and go away. Similarly, I can move this red one here above, but I have to flip it over the median as before. And if I do that, I'm going to end up with something that looks like this. And once again, I can have those two collide and disappear. And we end up with a much simpler diagram as we see here. Great. So I had a question about coboundary categories during Eugenia's talk, and here's the definition of a coboundary category. A coboundary category is once again a monoidal category with these natural isomorphisms between X tensor Y and Y tensor X. The difference here is that these ones have this nice property that CYX composed with CXY is the identity on X tensor Y. And then they also satisfy a different pentagon axiom, which is shown here. One kind of interesting fact is that braid and monoidal categories actually satisfy this diagram too, just by their normal definition. The only difference is that their commuter, their braiding, doesn't have this property here. In fact, if it does have that property there, it's precisely a symmetric monoidal category. And then this leads to the big theorem, which is that a category C is coboundary if and only if it's an algebra over this parenthesized cactus operad. And then I proved this in the style of Natalie Wall for strictly associative coboundary categories before realizing that Yao had done it in full generality in that same book on operads with group equivariance. And I think, wow, I timed that perfectly. Are there any questions?
Okay, let's first of all thank Olivia Borghi for their amazing talk. Silent applause.
Thank you.